In this lecture, I'm going to introduce you to one of the spatial filters that is commonly used in EEG data to help clean data and to prepare the data for connectivity analyses and so on. This particular spatial filter is called the surface Laplacian. It is also known in the literature as current source density or current scalp density or CSD. These terms are all used or can be used more or less interchangeably. I have also I have been guilty of using these terms interchangeably. After some thought, I settled on using the term surface Laplacian, so I recommend sticking to that term. But you will see these other terms in literature, and very often they are just different terms that refer to the same thing. So what is the surface Laplacian? The surface Laplacian is very simply a spatial filter that can be applied to the EEG data. I've talked, or nearly all of my lectures have been on temporal filtering. So applying different filters to the temporal characteristics of the data in order to extract more information out of the data than what you can get without temporally filtering. So the concept of spatial filtering is the same. You apply some spatial filter to the data that allows you to get more information out of the data than the spatially unfiltered version of the data. So here we have, a problem. So there's this phenomenon called volume conduction, which is the fact that the electromagnetic waves or fields that are generated when a population of neurons is active project to many or sometimes all of the electrodes or the MEG sensors that are placed around the head. So volume conduction is a bit of a double-edged sword, actually, because we need volume conduction. Without volume conduction, we would not be able to measure brain activity from outside the head, or at least we wouldn't be able to measure the brain's electromagnetic fields from outside the head. So in that sense, volume conduction is very good. But it becomes a problem because there's kind of, you could say excessive volume conduction. And this is a big problem for topographical localization. It's a big problem for brain localization, and it's also a big problem for connectivity analyses. And the problem there is that what we would really like ideally is to have a one-to-one mapping between the activity recorded at a particular electrode and some brain activity directly underneath that electrode. So you would really, we would like it to be the case that each electrode only measures activity from the brain tissue directly underneath that electrode. That would mean that every electrode is giving us an independent measure of a distinct region of the brain. Unfortunately, that's simply not the case, and there's no way to make it the case. So the idea of the Laplacian is to at least attenuate some of the volume conduction artifacts so that we can interpret the data a bit better. So I guess for EEG and MEG, there is both, for both these methods, there is volume conduction in the sense that the electrical field and the magnetic field are propagated from a brain source, which could be very deep in the brain, to all of the electrodes or the sensors. With EEG, but not with MEG, there is an additional source of annoyance for volume conduction, and that is that as soon as the electrical fields hit the scalp, or the border between the skull and the scalp, they also sort of spread laterally across the scalp. And this is a unique problem for EEG because magnetic fields go right through all these tissues unimpeded. So the idea of the Laplacian is that it is a spatial bandpass filter that you can apply to the data that will attenuate low spatial frequency characteristics. And here we have, so this is made up data. There's actually just random numbers, I think, that are smooth. But here you imagine this is space on this axis, so perhaps this is like the left ear going over to the right ear, and these are the different electrodes. So this would be kind of like waves over the space. And here, if you have your normal voltage map, you might see that the that the topography is dominated by one big low spatial frequency component. And what the surface Laplacian does is attenuate this low spatial frequency component, and that allows us to highlight the features that are present in the signal but might be harder to detect. Basically, it allows us to look at these anthills on top of the mountains by sort of getting rid of the mountains. Here's an illustration, and we'll repeat this simulation in MATLAB in a little bit. And basically the idea is that before applying the Laplacian, or without applying any spatial filter, the EEG topography is really dominated, or tends to be dominated, by low spatial frequency. And so by low spatial frequency, I mean dynamics that are really very broad and have a representation in many, or maybe even all electrodes. So, and then with the Laplacian, we can attenuate these lower spatial frequencies, and that allows us to recover higher spatial frequency activity, so more local activity, that is technically present in the unspatial, non-spatially filtered data, but just sort of more difficult to extract. So here you see an image of the estimate of the activity that is in the brain that is contributing to the activity recorded from a single electrode. So this is the brain, and this is like a mesh around the brain, and you imagine this one electrode here. And so what this picture is showing is this is the estimate of the amount of brain tissue that is, and with which strength, that is contributing to the signal that is recorded from this one single electrode. So you can see the electrode is most sensitive to the area of the gyro crown just underneath where that electrode is positioned. But also, you know, it's like a huge chunk of the brain is actually contributing to some extent to the activity that you can record with at this one electrode. Furthermore, if you look at connectivity, and this will be, we will see this again in the next module of lectures on connectivity. Connectivity estimates can be very strongly biased by distance, and this is because of the, let me go back to this slide here, this is because if you're measuring the connectivity between these two electrodes without applying any kind of spatial filter or without doing any special connectivity analysis that accounts for volume conduction, basically you're going to see an extremely high estimate of connectivity between these two electrodes, but a lot of this is going to be an artifact and attributable just to the fact that these two electrodes are measuring the same activity from exactly the same source. So this is problematic. So what they're showing here, this is simulated data, is that when the distance between each pair of electrodes increases, so this is inter-electrode distance, the connectivity, the apparent connectivity between those two electrodes increases with decreasing distance between them. Here they show a sort of resurgence. You don't see this in real data, but this is actually just simulating that you get to the other side of the dipole when you get far enough away. Okay, so now the idea of the surface Laplacian is that by filtering out a lot of the low spatial frequency components, you are highlighting more the local features in the data. And so, yeah, I mean, this is just an illustration, but the idea is that each electrode is measuring each electrode is measuring more selectively a smaller region of the brain of cortex that's directly underneath that electrode. So this is not to say that the Laplacian completely eliminates volume conduction, but this is the idea. It certainly attenuates volume conduction by getting rid of these low spatial frequency components. So here we see the other part of this slide, this figure from the Srinivasan paper. So here you see after the Laplacian, only a very confined patch of cortex really contributes to the activity at this electrode. So this is simulated data, but this you can think of as, you know, your your internal model, your understanding of the effect of the Laplacian. That basically we're going from a situation where each electrode measures activity from a considerable portion of the brain to a situation where each electrode measures activity maximally or is maximally sensitive to activity from a relatively restricted part of the cortex that's mainly coming from the gyro crowns of the tissue that is closest to each electrode. Okay, and so here, coming back from this other part of the simulation, so here they show that with the Laplacian, the connectivity decreases very precipitously as a function of interelectrode distance and does not resurge later. We will also see this in empirical data, in real data, later on, and it generally looks pretty much like this. This is the same thing for MEG. Here is yet another simulation. There'll be quite a few simulations in this lecture, but also some real data. In this simulation, the authors simulated dipoles in the brain. I don't know if they intended to make it look like a face, but it does anyway. With different strengths and different orientations of the dipoles and things like that. The important part is to compare what you would measure with EEG and then the Laplacian of that, and this would be the cortical potential. This is, as if you were, you could have your electrodes under the skull, on top of the brain, on top of the dura, as if these were like epilepsy, recordings in epilepsy patients, for example. And then this was another simulation with different strengths of the dipole. And what you see is that the Laplacian is a pretty good estimate of what the cortical potential would look like. So what the EEG would look like if you were measuring from underneath the skull. Of course, this is simulated data, so it looks very good here. So here is actually real data. Here is the voltage map, so this is before applying a spatial filter, and this is the same data with the Laplacian. And what you see, if you look carefully, you can actually see that a lot of the dynamics are present, sort of topographical features that are present in this map are also present in this map. Really what's different is that this voltage map before applying the Laplacian is really dominated by one single huge low frequency component that's this massive blue thing that is really just dominating pretty much the entire topography. And what the Laplacian does is remove that low spatial frequency component of the data, and that allows you to better visualize and quantify these higher spatial frequency components, these more local components. And again, if you look carefully back and forth, you can see that all of these features are actually in here. They're just harder to spot. So this is a striking example where you see a huge difference between before and after applying the Laplacian. Here's a different example showing before and after applying the Laplacian. You can tell I made these slides a while ago. That's why they say CSD. In this case, the map has changed very, very little after applying the Laplacian. And the reason why there's so little change here is because this map already was dominated by higher spatial frequency components. You can see there aren't really many low spatial frequency components in this map. And so applying the Laplacian actually didn't really have a huge effect. Of course, it does change something. Anytime you apply an analysis or a filter to your data, something will change. But the qualitative differences are very minimal. So what I wanted to highlight here is that it's not necessarily the case that the Laplacian is really going to qualitatively change your data. It will only qualitatively change the data when the data are really dominated by low spatial frequency components, very broad topographical components. Here we see some real data. This is the ERP, so time domain average, and this exact figure we will recreate in a few minutes in MATLAB. So here you see different latencies, and the top shows the voltage data before spatial filtering, and then the bottom shows the Laplacian. And I think it's very interesting to compare these two sets of maps, because these are really the same data, just with and without any spatial filtering. And it's quite one of the things I find very striking is this right posterior visual component, which is really difficult to see. You can kind of see it here, but by this point, this component is relatively small compared to this these larger low frequency components. And so you don't really get a chance to see this right lateralized posterior stuff in here. Here's an example here where you see that the Laplacian sharpens the data, but otherwise doesn't really change the features so much. That's because this is a relatively lower spatial frequency signal. I would also like to mention that when you are at the quote-unquote source of the activity, the Laplacian won't really change the data very much. So I have to define this term source, because when you use the term source in EEG or MEG, people often think that you're talking about some kind of brane localization, like a dipole localization, or some kind of distributed localization procedure like M&E or beamforming. In this context of the Laplacian, we can talk about the topographical source of the activity. We're not necessarily making any inferences about exactly where in the brain the signal is being generated, but we're just using the term source to identify the electrode where the topography is maximal. So here we can say this electrode here, FCZ, this is the source of this feature, this topographical feature, in the sense that, it shows the strongest activity here in the Laplacian. So the Laplacian is acting to sharpen the data, and it will help us identify where on the scalp the signal is really coming from. So I said that at this electrode, when you're at the source electrode, the topographical source electrode, the Laplacian has very, very little effect on the data. And that you can see here. These are time frequency plots of the data with the Laplacian and without the Laplacian. And it's really difficult to see any differences. So you can look here. Okay, there are, of course, some differences. The data are not identical, but the qualitative pattern is exactly the same. And the conclusion you would come to about the relationship between brain and behavior in this task would be the same with or without using the Laplacian. This is only the case because I'm plotting the data from the source of the topographical source, the key electrode here. If we were to pick, for example, this electrode, you could see that at this electrode, before applying the Laplacian, we would get a much stronger influence from the source, so from volume conducted activity. So if we were to make time frequency plots at this electrode, that would look quite a bit different before versus after applying the Laplacian. Here's just another illustration of some ERPs and some phase angles. I think this was, it must have been sort of gently bandpass filtered. Oh, it was filtered from 2 to 20 hertz. And the connectivity and estimate of time-varying connectivity between these two electrodes. So I think these two electrodes were FP1 and FP2. I made this figure a very long time ago. But I intentionally selected electrodes here that were very physically close to each other. So it looks like the connectivity is very high, it's close to 1. I mean, visually you see it looks like these two electrodes are really doing basically the same thing. But that's really because of volume conduction. So these two electrodes are measuring activity from the same sources in the brain. But now when we apply the Laplacian, we can see that the Laplacian has helped to decouple these two electrodes. So even electrodes that are very close to each other now are only very weakly correlated with each other. They show only very weak connectivity. This is an issue that we will get back to in the next section on doing connectivity analyses in EEG and the importance of the Laplacian for connectivity analyses. Okay, so how does the Laplacian work? We can think about this kind of lateral spread of the electrical potentials at the skull-scalp border. And then we can think about, how we might go about addressing volume conduction and subtracting the volume conducted activity from the electrodes. So imagine we have, just 5 electrodes here, and what we want to do is eliminate or attenuate the volume conducted artifacts that are shared across all of these electrodes. So you can imagine that one way to think about this is that any activity that we see equally well at all of these electrodes, this is going to be activity that is shared across all the electrodes, and that is going to reflect volume conducted activity. So what we can do is sum all of these electrodes, or take the average of these surrounding electrodes, and subtract that average from the activity at each individual electrode. This is fine. This was like the old school method of doing CSD, and it's called the Hjorth method, I think from the late 70s or maybe even earlier. So that's okay. This is like a poor man's Laplacian. But of course, there's 2 limitations here. One is that, of course, we have more electrodes on the head. We have lots and lots of electrodes, dozens or maybe even a few hundreds of electrodes on the head. And another problem is that, or another limitation is that the spread of the voltage is going to, or the spread of the electrical field is going to decrease as a function of distance. So we wouldn't necessarily want to weight the signal from this electrode the same as we would weight the signal from this electrode. So what we would want is to have a way to compute the Laplacian that incorporates all of the electrodes, not only the surrounding electrodes, but all the electrodes, and also somehow accounts for the distance from, that distant electrodes will affect the electrode under consideration less than electrodes that are closer by. So, and this is the idea of the Laplacian. I won't really get too much into the details of it, but it involves basically computing two separate matrices that code for distance between each or among each pair of electrodes. And then these 2 matrices act as the filter through which all the data are passed in order to compute the Laplacian. So there are 3 main reasons why you would want to use the Laplacian in your EEG data analyses. One is for topographical localization, and that is basically what I highlighted here, where you want to say that this activity, this entire feature in the data is localized to this electrode. And again, that doesn't necessarily mean that this EEG activity is localized to the brain tissue directly underneath that electrode. That's a little bit more tricky to say. But we can topographically localize the activity to a single electrode. So that's one motivation for applying the Laplacian. Another motivation is to do connectivity analyses. This we will talk about more in the section on connectivity. And also just to clean the data. So people are now increasingly showing, and you might often see this in your own data as well, that simply applying the Laplacian will increase the signal-to-noise ratio of the results. I don't think this is something that's kind of mathematically necessarily the case, but it does seem empirically to happen very often. So I think you will often find that your results just look better and cleaner if you apply the Laplacian compared to just doing it on the raw voltage data. Technically, the units are different after the Laplacian, so they are microvolts per some measure of squared distance, so centimeters squared, or depending on how you scale the data, some people also plot microvolts per meter squared or per millimeter squared. If you're doing time frequency analyses, I typically recommend converting the data to decibel or percent change, some kind of normalization. And so then you don't really need to worry about the original units, because the ultimate units will be some kind of normalized factor. Okay, so here we have another example, and we're going to generate this figure in a few minutes. So here I simulated a low spatial frequency component, two high spatial frequency components. When you sum them together, this is like what you would normally see in your EEG data. You have all these different components in the brain that are generating activity. And by the time you measure them, you get the summed activity. So if you would just see this panel C in your data, you would probably conclude that there is one big, large, sort of central parietal source that is contributing to, or that is driving the EEG data. But if you apply the Laplacian of this topographical map, then you see that this low spatial frequency component is not entirely eliminated from the data, but really, really strongly attenuated. And what you get back is the high spatial frequency, the more kind of local dynamics. So that's very nice. There are a few sort of, you could call them limitations or disadvantages of the Laplacian. One is that by definition, all the deep sources are lost. This happens by definition because deep sources will contribute to many, many electrodes, to the activity you record from many, many electrodes. And so what the Laplacian is going to remove from the data or attenuate from the data are very deep sources that are contributing to many electrodes. So this can be a disadvantage if you are hoping to find fairly deep cortical sources with your EEG. So one example would be like this is sort of, this isn't too deep, but sort of deep anterior cingulate, or the insula, or the posterior cingulate. These sources in the brain that are relatively far away from the skull, they will produce lower spatial frequency features in the data, and so they will be lost, or at least very difficult to recover with after applying the Laplacian. For this reason, it's actually possible that you can fail to replicate some findings just because you're using the Laplacian. And one example that people often use is the P3B. So the P3B is this central parietal component that you see in EEG data when people are you see it in many, many sort of cognitive tasks. But the P3B is it's a very big, broad, widely distributed component, and the Laplacian is actually very good at getting rid of the P3B from your data. So if you're trying to do a P3B study, then the Laplacian is probably not the best thing to do to your data. It's not the best spatial frequency to apply, or spatial filter. Another limitation of the Laplacian is that the algorithm is purely based on the inter-electrode distances. It's not based on the actual data. And it would be nice in theory if you had a method that would change the characteristics of the spatial filter, not only according to the electrode positioning, but also according to what's actually happening in the data. So here you would, in this situation, you would want to apply a stronger filter, and here, these deep sources are less, maybe these electrodes are less strongly intercorrelated, so then you would want to dampen the effect of the spatial filter. There are other spatial filtering methods that do incorporate the data covariances, like beamforming, for example, but the Laplacian is a fairly simple method that does not incorporate the actual signal characteristics. So let's see how some of this looks in MATLAB. We can load in the data, and here, this first cell is just going to generate the maps that we saw in the PowerPoint slide. They're nicer looking here because they're in color. I encourage you to play around with this code in case you are ever interested in simulating topographical data. This can also show you how to generate these kinds of topographies. This is not a very sophisticated EEG simulation. You know, I'm not really simulating any sort of temporal dynamics or anything. All I do is define Gaussians based on interelectrode distances from each of these seed electrodes. So, and you can try, if you look on like lines 37 and 38, you can change the width of the filters to see how that affects the results. So we can make this, yeah, we can just make this much bigger. I just now noticed that this whole thing is backwards. Sorry about that. In the version you will download, this will look better. The high and low is mixed here. That's funny. I'll fix the rest of that later. And then if you run the second part of this script, this will produce this sort of array of topographical maps that I also showed in the PowerPoint slide. So you can change the time points if you want. There's also a function that you will need that actually implements the Laplacian, which is called Laplacian paren. X, the paren is for the first author of the paper in the late 80s who first introduced this method to the EEG field. One final thing that I forgot to mention is that the Laplacian should only be applied on time domain data because there are assumptions about the polarity of the signal. So you should not apply the Laplacian on time frequency power or phase or connectivity data or anything like that. The Laplacian should only be applied to the time domain signal. In fact, I apply the Laplacian basically as the final step of pre-processing the data. Okay, so that was it. I hope you enjoyed it, and I certainly encourage you to experiment with the Laplacian. I think it's a very simple but very powerful spatial filter that has really often surprisingly nice effects on the quality of the EEG data.